CB89, CB89, okay, 88 has joined just now. Okay, 88 has joined now. Okay,
Yes, ma'am.
okay, 89, ETB 35, you mute. ETB 35, mute. CB 92, CB 92, CB 93, CB 93, CB 94, CB 94, CSB 60, Computer Science 60, Computer Science 61, CSB 61, Computer Science 63, 63. I just again tell you that I am calling only the absent roll numbers. That means the remaining students are present. To save time, I just call only the absent roll numbers. Computer Science 70. Computer Science 70. ETB 41. ETB 41. Electronics 41. EB 55. Why have you sent your attendance to chat box? Electrical engineering 55. Why have you sent your attendance to chat box? I did
Ma'am,
not call.
I just joined. That's why I don't
Okay,
know.
but I have checked twice and then I did not call your roll number.
Okay, ma'am.
Okay. ETB 41. Electronics 41.
Ma'am, CEB 089 present.
Also ITB 059 present.
No, you cannot call, you cannot tell this or your roll number in middle of this. No. If it is finished, then you may tell. Otherwise, it creates lot of problems. Okay. When it will be finished, then you will tell me. It is really. Wait. ETB 41. ETB 41. Electronics 41. IT 56. IT 56. IT 56. I think I have called this whole number IT 56. Okay. Mechanical engineering 49. Mechanical engineering 49. Metallurgy 30 30. MMB 30 30. Mining 26. Mining 26. Okay, I have called the absent roll numbers. Is there any student who has
Ma'am,
joined?
ma'am, I am IT B07, B057.
IT 57.
Ma'am, CSB
Just a
061.
minute. Oh, just a minute. IT 57. Yes, I have given you attendance already. Next, CSB 61. Who was talking?
Yes, ma'am, CSB 061.
Okay.
Suman Kumar.
CSB 0.
Ma'am, CEB 089.
Just a minute, please. Computer science 61. Yes, I have given just now. Next,
Ma'am, AMB 028, ma'am.
MB 028. Okay, I have given now. Okay, any more?
I'm
Please,
electrical 55.
electrical 55.
Yes, ma'am.
Electrical 55. Just a minute. Electrical 50 I have already given. Okay.
CEB
Okay, ma'am.
089.
CB 089. Okay. Now I have given. Any student
Okay,
more?
ma'am.
Please let me start.
Ma'am, IT 59.
I think you have already told me. Why are
Ma'am,
you
but then
repeating?
you asked me to shut up, so I.
ITB 59.
Yes, ma'am.
Ma'am,
ITB
AMB,
59 already given. Don't repeat, please. Don't waste time.
ma'am,
Okay.
AMB 025.
AMB 025. You have just joined. Okay. Next, any more? Please tell me. Okay, let me start now. Otherwise, it will be class of attendance only. Okay. I will share the screen now and then I will start. I think I have sent the course material of previous class and all of you have received. So today I will start just a minute sharing the screen. Is it visible?
Yes, ma'am.
Yes, ma'am.
Okay,
Yes,
okay.
ma'am.
Okay, now we start. Already we have discussed that if the differential equation is of this form, just you consider this differential equation of order n. Nth order ordinary differential equation is this, where you know the notation capital D stands for ddx. And in the previous classes, we have considered the equation, differential equation, whose right side is 0. Already it was discussed the differential equation where the right side is 0. We have firstly write down we have written the auxiliary equation and then find out the roots of the auxiliary equation, and after that, depending on the nature of the roots of the auxiliary equation, the general solution will be different, right? All these things are known to you. Important thing is this: the right side was 0 in the previous differential equation already discussed in the previous classes. Is it known to all of you, right? Where we have written the auxiliary equation. After that, we have computed the roots of the auxiliary equation. And if the roots of the auxiliary equation be real and distinct, and also if the roots of the auxiliary equation be real and equal or complex conjugate roots, we can write down the general solution of the differential equation whose right side is 0. Today we will discuss the differential equation whose right side is non-zero. This is the difference between the previous method and today's method. Okay, where the right side is capital X, where capital X is a function of small x only or maybe constant. Okay, but
Ma'am,
in
start the
order to
recording, please.
who someone was talking, please tell me.
Ma'am, start the recording.
No, it is not required to record these things. Is there any problem?
No, ma'am.
I think you please concentrate on this topic, and after that I will send this all this course material to all of you. I have written each and every step in the course material, so it is not required to record. But I request you to concentrate on the topic, and if you face any difficulty, please tell me. That will help you as well as me. Okay, if I record and then if you I provide this, send this, then there is no importance of this class. I think so. Is it clear? You please concentrate on my teaching, and if you face any difficulty, call me, tell me, and I will send all this course material, class materials to all of you. I have written each and every step in this course material to help you. Okay, is it clear?
Yes, ma'am, sure.
Hello,
Yes,
Shumit.
ma'am.
Is it acceptable to you?
Yes, ma'am. Thank you, sir.
Okay, if you face any difficulty, please tell me.
Okay,
Okay,
ma'am.
that will help us.
Okay, ma'am.
Okay. Now you see the differential. We consider here the differential equation whose right side is non-zero. And you see this is capital X. Here capital X denotes a function of small x only, or it may be a constant. Now what is done in this situation? We first solve the differential equation whose right side is 0. You see equation number 2. We first solve the differential equation whose right side is 0. That means the method which have been discussed in the previous classes. And suppose y equals to phi x is the general solution of the differential equation whose right side is 0. That was discussed in the previous classes. And new thing is this: y equals to phi x is a particular solution of the differential equation 1. So to compute y equals to phi x is new in this chapter.
Ma'am.
So to compute phi x, which is the general solution of the differential equation, I think someone was talking. Who was
Ma'am,
talking?
can you mark me present? I was not able to join the class because of current issue. Now I have joined.
But can you disturb me during this class? Is it possible? Then whole time throughout the class I will take your attendance only. Someone may join after 15 minutes. You please wait. You concentrate on my teaching on this topic. After that you may tell at the end of the class. I request you to all of you, someone joins late. Yes, it may happen. Network issue is a serious issue.
Sorry,
We
ma'am.
have nothing to do. Plus, please, but I request you to all of you, please, let me continue to teach these topics. Otherwise, I cannot finish the syllabus. That will create lot of problems to you. If you have missed, okay, I will give you your attendance. Don't worry. But you please tell me after this, at the end of this class. During this teaching, please don't disturb me.
Okay, I'm sure.
Okay, you are civil engineering 94.
Yes, ma'am.
Okay, I am giving. Yes, I have given now.
Thank you, ma'am.
Okay. Now you concentrate on the topic. Okay.
Okay, ma'am.
Okay. You see, the solution phi x, which is actually the general solution of the differential equation whose right side is 0, already discussed in the previous classes. And new solution is phi x, which is called particular solution of the equation 1. Finally, it can be proved that this phi x, which is the general solution of the equation whose right side is 0, plus phi x, which is the particular solution, this y equals to phi x plus psi x is a general solution of the differential equation 1. I am telling you that here, that means in this chapter, we are to find out the general solution of an ordinary differential equation whose right side is non-zero. And already we have discussed the method of solving the differential equation whose right side was 0. And here in this theorem, we can show that if phi x is the general solution of the differential equation whose right side is 0, and psi x is the particular solution of the differential equation 1, then phi x plus psi x is the general solution of 1. Okay, I think it is known to all of you why is it called the general solution. When is it called general solution? Phi x, which actually already you have observed that phi x contains arbitrary constants. And you know, in the general solution, the number of arbitrary constants is equal to the order of the differential equation. That means if it is nth order differential equation, you see, then its general solution, if y equals to phi x is the general solution, then this general solution should contain n number of arbitrary constants. Okay, now you see, how can we prove that phi x plus psi x is a solution of the differential equation 1? You see, we have assumed that phi x is the solution, general solution of equation number 2. What does it mean? Phi x is a general solution of 2 means if you replace y, if we replace y by phi x, then equation 2 will be satisfied. That means you can replace y by phi x and then you obtain this. You see, just we have replaced y by phi x because phi x is a solution of the equation 2. Next you see phi x is a particular solution of 1. That means psi x, this if we replace y by psi x, then the equation will be satisfied because here we have assumed that psi x is a particular solution of 1. So we may replace y by psi x and then equation 1 will be satisfied like this. Since y equals to psi x is a solution of 1, then you see this equation. We obtain this equation just replacing y by psi x. Now we can add 3 and 4. Then what we get? This. We get this. What is it? You see, just y is replaced by phi x plus psi x in equation number 1. If we replace in 1 this y by phi x plus psi x, then you will obtain equation this. If you compare this equation with 1, what is your observation? Just y is replaced by phi x plus psi x. What does it mean? It means that equation 1 is satisfied by y equals to phi x plus psi x. And so it is proved that y equals to phi x plus psi x is a general solution of 1. Why is it called general solution? Because you see there exists phi x, which is actually general solution of equation number 2. That means phi x contains a number of arbitrary constants. And phi x is included in this solution also. So phi x plus psi x, which contains a number of arbitrary constants. So it can be taken as the general solution of equation number 1. Why is it solution of 1? Because we have obtained an equation like this where y is replaced by phi x plus psi x in 1. So it is proved that y equals to phi x plus psi x is a general solution of So equation 1 is satisfied by y equals to 5x plus psi x, and so it implies that 5 plus psi x is a solution of equation number 1, and it contains a number of arbitrary constants. Actually 5 contains a number of arbitrary constants, and so 5 plus psi x also contains a number of arbitrary constants. So 5 plus psi x may be taken as the general solution of 1. Yes, this 5 is called, this 5 is called complementary function. Just this 5 is called complementary function, and psi x is called particular integral. You see, in short it is written as c dot f dot complementary function. This phi x is called complementary function, and this psi x is called particular integral, and in short we may write cf pi. So here the general solution equals to cf plus pi. What is cf? Cf is actually phi x. What is phi x? Phi x is the general solution of the equation whose right side is 0. You see, phi x is the general solution of this equation number 2. What is psi x? Psi x is the particular solution of equation number 1. Already we have discussed in the previous class says that how to compute phi x, but in this chapter we have to compute psi x. Okay, there will exist some short methods by which we can find out psi x, which is called particular integral. Now, in order to find out this psi x, some symbols may be required. Suppose 1 by fd. Already it is known the notation d. D stands for ddx. And what does it mean? This operator 1 by fd. Actually, the symbol is self-explanatory. It is inverse of fd. Inverse of fd, right? Now you see, suppose we consider this differential equation. Just take an example to explain this symbol. You see, this is fd. Fd means we are function of d only. D square minus d. This is function of d. Operating on this equals to this. So 1 by fd means actually 1 by d square minus d. Then you see 3 minus 2x equals to x square minus x. Just you see this example where you can actually imagine what is 1 by fd. If it is fd, d square minus d operating on x square minus x gives 3 minus 2x, then 1 by fd operating on 3 minus 2x will give x square minus x. If we consider fd equals to d, d means ddx, that is derivative with respect to x, then 1 by fd means 1 by d, that is actually inverse operator of d. You know d stands for ddx, that is differentiation with respect to x. So 1 by d is an operator which is inverse process of differentiation. So it should imply integration with respect to x. So 1 by d stands for integration, where here capital D stands for differentiation with respect to x, and hence 1 by d, it is the inverse of d, that is inverse process of differentiation, so it implies integration. So here we can prove that 1 by fd operating on x is the particular integral of this fdy equals to x. You see, this is the differential equation fdy equals to capital X. This is the differential equation.
Ma'am, I have a question, ma'am. Can I ask?
No, at the end, you please just remember this
Okay, ma'am.
question.
Okay, ma'am.
Please let me finish. After that, you may ask. Okay? Otherwise, I cannot finish. Okay. You see, fd here, fd is actually function of d. Okay. So I am telling you 1 by fd operating on x, that will be the solution of 1. 1 means, you see, this equation. Just you see. Actually, this is fd, function of d, operating on y equals to x. This is equation number 1. If you use the notation fd, then this is fd, function of d. Then operating on y equals to capital X. Now you see here, just you see, 1 by fd operating on x is the particular integral of fdy equals to capital X. What we do here, you see, You see, 1 by fd operating on x will be the solution of 1 when it will be called the solution of 1 if it satisfies the equation 1. This 1 by fd operating on x, this will be the solution of the equation 1 if it satisfies 1. Then how can we prove that it satisfies 1? Just we replace y by this. If we replace on the left side y by 1 by fd operating on x, and then if we get the right side, then equation 1 is satisfied. What is done in order to prove that whether the equation is satisfied by this or not? Just we replace this y by that 1 by fd operating on x like this. Just you see this. If we replace y by 1 by fd operating on x, you see, if we replace y by this in equation number 1 on the left side of 1, and if we obtain this x, you see, that means it is x equals to x. That means left side equals to right side. What does it mean? That means equation 1 is satisfied. So it 1 by fd operating on x is a solution of 1, which is called particular solution. Now I will describe some short methods for finding this particular integral. First of all, you see 1 by fd operating on x. That means this particular integral depends on capital X. What is it? Capital X means the right side function in the differential equation. Okay. Capital X is actually, you see, the function on the right side of equation 1. So particular integral depends on this function lying on the right side. You see, capital X is the function on the right side, and you see particular integral, you see particular integral is 1 by fd operating on x. This is the particular integral, so it depends only on capital X. Okay, it depends it depends on capital X. Okay, now there exist different forms of capital X that will be discussed one by one. Suppose capital X is a function of e to the power ax, that is exponential function where a is some constant. Just you see, capital X, that means the function on the right side is an exponential function where you see a is some constant, e to the power x where a is some constant. Then this is actually the formula for finding the particular integral where capital X is an exponential function like e to the power ax where a is some constant. Consider this. Particular integral means, 1 by fd operating on capital. Yes, this is called particular integral. Now, x will be different. X may be different in different problems. And depending on the nature of the function capital X, the formulae will be different. There exist different formulas depending on capital X. That means depending on the nature of the function on the right side. First of all, we observe that capital X is an exponential function like e to the power ax. Then the formula is this: 1 by fd, capital X is replaced by e to the power ax. Now you see the formula gives this, just d. D means you see this d is replaced by a, where a is the coefficient of x in the exponential function. Provided you see the denominator is non-zero. This is the formula for finding the particular integral where the right side capital X is e to the power ax. Just you see this application in this problem. Suppose the differential equation is this. You see, here fd means this is fd operating on y equals to exponential function on the right side. This is actually the capital X. This is capital X, the function on the right side. And you see, all these are functions, all these functions on the right side are exponential functions. So we can use the formula number 1, particular integral for finding this, you see, number 1, formula number 1 to find a particular integral where the right side function is exponential function like this. You see, in order to find out the solution of this differential equation whose right side is non-zero, we have to compute phi x as well as psi x. Phi x, how to obtain phi x? Just consider the right side equals to 0 and solve the differential equation by using the method already discussed in the previous classes. And here we are to find out Chi-x, that is called particular solution, and that can be computed using some formulae that is discussed now one by one. So we first compute the solution whose right side is 0. So you see, consider this right side equals to 0. So the differential equation looks like this. And then you see we are to find out the general solution of this differential equation by writing down the auxiliary equation. And it is already known to you how to write down the auxiliary equation. It is a simple formula just by replacing d by m, where y equals t to the power mx is a trial solution of the differential equation. So by replacing d by m, you can write down the auxiliary equation. And now we solve this auxiliary equation, and we observe that all the roots are real and distinct. If all the roots are real and distinct, then you know the formula should be C1. Suppose these are M1, M2, M3, which are real and distinct, and so the complementary function is actually general solution of this equation whose right side is 0 is called complementary function, that I have already told you that phi x is called complementary function. You see, phi x is called complementary function and psi x is called particular integral. And actually sum of these two, that is complementary function plus particular integral, will give the general solution. So you see please that we have just computed the complementary function. That was the method. We have used the same method already discussed in the previous classes. I think it is already discussed. Now we are to find out the we are to find out the particular integral. So just we simplify the right side function, that is capital X. You see, just simplify this and obtain this. You know cos hyperbolic x, by definition, cos hyperbolic x in exponential function, in terms of exponential functions is this: e to the power x plus e to the power minus x all divided by 2. And just simplify this and obtain this. Just simplify this and obtain this. All these are exponential functions of the type e to the power ax. Then we are to find out the particular integral. You know particular integral is actually 1 by fd operating on capital X. This is actually capital X, that is the function on the right side. Already you have observed that the function on the right side is this. This is capital X. Now it is, you see, capital X. And 1 by fd means 1 by this. fd means this. fd means this. So it is actually, you see, fd means this. You see, this is fd. Already it is known to you. This is fd. And fd has been just resolved into linear factors, and it is known to you that these are the factors. So the factors should be like this: d minus 1, d minus 3, d plus 2. Okay. Now you have simplified this, and already we have computed this equals to this. Just to write down, just replacing this by this, you can replace this by this simplified form. And so this is fd, this is capital X. So what is, and this is actually exponential functions like this. And you see, this is sum of three exponential functions. So we can break this into sum of three terms like this: 1 by this operating on e to the power 4x, then 1 by this operating on e to the power 2x, plus 1 by this operating on this. Just you see. Now what does it mean? What is the rule? You see, just d will be replaced by a, provided, you see, a is the coefficient of x in the exponential function. So you see why we have just separated all these three terms, because you see in the first case the coefficient of x in the exponential function is 4x. In the second case, coefficient of x is 2. In the third case, coefficient of x is 0 in the exponential function. So these terms should be separated like this, like this. And so d will be replaced by 4, where we consider this term, the coefficient of x in the exponential function is 4. So d will be replaced by 4, you see. D has been replaced by 4. In the second term, you see the coefficient of x is 2. So d will be replaced by 2 like this. And in the third term, you see the coefficient of x is 0. So d will be replaced by 0. And we obtain this. Just you see, or in all these three terms, since the coefficient of x is different in different terms, so for we see in the first term coefficient of x in the exponential function, so d will be replaced by 4 in the first term. In the second term, 2 is the coefficient of x in the exponential function, so in the denominator d will be replaced by 2. In the third case where the coefficient of x is 0, so in the third case, in the third term actually d will be replaced by 0, and then we obtain this. This is called particular integral. And finally you have to add the complementary function and particular integral to obtain the complete solution or general solution. Already we have computed the complementary function, and now we have just computed the particular integral, and we have to add this and this to obtain the complete solution of the given differential equation. Okay, CF plus PI is the solution, which is the complete solution of which equation? You see, complete solution of this differential equation whose right side is capital X, which is a function of X or constant. That is non-zero. In this chapter, we have to consider the differential equation whose right side is non-zero. And in order to solve this type of differential equations whose right side is non-zero, we are to first solve the differential equation whose right side is 0, and additional computation is to find out the particular integral. That is additional computation will be done in this chapter, but the function on the right side is like this, say capital X, which is non-zero. Now you ask, someone was asking, probably 77 CV. Are you asking?
Yes, ma'am. Actually, ma'am, the D means, ma'am, dy by dx.
No, no,
So,
no. D means ddx, not y. D means an operator. It will operate some function. D
okay, ma'am.
means
Then
operation.
how 1 by d equals to a integral sign? 1 by
Because
d should
just
be.
you see the conception. What is the concept behind it? That is important. Capital D stands for ddx. That means it is a differential operator. Okay. And so 1 by d, conceptually, it implies the inverse process of differentiation. That is mathematically called integration. And so we just use this operator 1 by d as an operator which will integrate. Because capital D stands for ddx, which implies it is a differential. It implies the process of differentiation. D stands for the process of differentiation. And so if 1 by d stands for the inverse operator of d, that means it implies conceptually inverse process of differentiation, which is in mathematics called integration. This is the conception. And you use this conception and then you use this symbol. And since D stands for ddx, that is derivative with respect to x, and so 1 by d stands for integral with respect to x. And so you use, just a minute please, just a minute, I am showing this, just a minute. You see here 1 by, you see if fd equals to d, so 1 by d operating on x, that means 1 by d, which is actually the inverse of d. D implies actually differentiation, so 1 by d implies integration. This is the concept. And so we use this symbol integral operator, and since d stands for ddx means differentiation with respect to x, so 1 by d should stand for integral with respect to x, and so we have written this integral dx, and it operates on capital X, so it is written as capital. Suppose it is 1 by d operating on, say, it is x square. Say x square, capital X is x square. So integral x square dx,
So
that is
then
x
it should
square.
be integral x squared dx.
Yes, yes, yes. That means capital X, this capital X is actually the integrand. Okay? That means the
Yes,
function
ma'am. FX.
on which integration will be applied. This is actually integrand. Capital X will be the integrand like this. Okay? Is it clear?
Okay, ma'am. Understood.
Okay. Okay, thank you all of you. Now I leave and I will send you this portion to all of you. Thank you all of you.
Thank you, ma'am.
Okay, tell me. I
Yes, ma'am. वो attendance.
56 IT.
Yes.
You have joined late.
Yes, ma'am. Due to network problem.
IT 56. Okay, okay, okay. ITB 56. Okay. I have given just now. Okay. Thank you. I have
Thank you,
given
ma'am.
now.
Thank you, ma'am.